Bit of a challenge here. We're going to be talking about something called nuclear fission and nuclear fusion. And unfortunately, the words are very, very similar. But put the phone away, kiddo.
I'm using it to do something.
Can you actually do the notes right now, though? Okay. If you look at your green sheet, okay, if you look at your green sheet, folks, on the bottom of your green sheet on the front page, I put the difference between nuclear fission and nuclear fusion.
Why did you put it on the top like that?
Put what on the top?
Like the name thing.
The name thing on the top of what?
On the top of the page where you put your name. It's like, just put it there, bro.
Oh, it just did that when I did the headers. Sorry about that. Yeah. So what I want you to notice, though, Sadie, is on your green sheet at the bottom right here, I have the difference between fission and fusion because it's easy to get them confused.
Splitting atoms.
Okay. So, nuclear fission is the splitting of one nucleus into two smaller ones. You may have heard the term split the atom, and this is what we're talking about in nuclear fission. The word fissure or fission means to break apart. A fissure in the earth is a crack in the earth, so a crack in an atom. You also get some subatomic particles, but most importantly, you get energy in the form of heat and light. And so this can be used to generate, quiet please, electricity. It's that subatomic particles that actually ends up being quite important. Nuclear reactions. So in nuclear reactions, we have new atoms produced. So new atoms are produced. So you end up with different elements than you started with. But it's the same rules as balancing those other decay and radioactive equations, where the sum of the charges, which are the bottom numbers, and the sum of the masses, which are the top numbers, have to stay constant. I know it's different on your periodic table. It's just unfortunate. It's the notation. So we have several different types of subatomic particles that we can use in nuclear reactions. First of all, we have protons. When we're using our particle notation, we write them like this. We use a lowercase p. They have a mass of 1 and a charge of 1. So we often write them as 1p1. I put that on your green sheet.
It looks like those.
Okay. Is that a stretch or a hand up? Okay. There's another way that you'll sometimes see a proton written. Technically, a proton is a hydrogen nucleus. And so sometimes you'll see it written as 1H1. I put both of them on your green sheet under radioactivity symbols. So we have protons. What's another subatomic particle?
Neutrons.
Okay, so another thing that's given off in nuclear reactions are neutrons. In our atomic mass notation, they have a mass of 1. N for neutron, they have a charge of 0. So there's our symbol for neutrons. Good morning, good morning. I'm glad you made it. Thankfully for the nucleus, There's no other way to write it. There's not a second way. So yay. What's another subatomic particle? I heard it. Electrons. And so electrons are written either as 0, -1 e, but these are also beta particles. And so you may see it as 0, -1 with that beta symbol. What's the 0 mean? They have a mass of 0. They're really, really lightweight, so we ignore their mass. -1 is their charge. Okay. And the last one that's given off isn't exactly a subatomic particle, but it happens during nuclear reactors. It is alpha particles. So alpha particles, which were a mass of 4, symbol that little fish, 2. But they were also sometimes called a helium nucleus. Well, it's kind of a flip-flop between the two of them. So,
but it's like you put the particle symbol in there, or you put the helium nucleus.
So if you want to, you can put that there, and if you want to, you can put that there, because the helium nucleus symbol was the 4He2. You're right. I probably should have flip-flopped those. I agree. It is. Candy for you later. Can you remind me? Okay. So we have 4 particles, technically 3 subatomic particles and 1 alpha particle, that can be given off during a nuclear reactor, during a nuclear reaction. And it was thought that if you could fire these at an unstable nucleus, that when it hit the nucleus, it might cause the nucleus to split. This was the thinking in the 1930s. It was, okay, maybe we can split an unstable atom by basically firing a nuclear bullet through it. Well, electrons have so little mass, it was thought electrons won't do it, but maybe a proton would. It's got enough mass, or an alpha particle. There was a problem with protons and alpha particles, and the problem is both protons and alpha particles, don't write this down, are positively charged. And so when they got close to the nucleus, they got repelled. Which of these 4 particles has some mass but no charge? Which of these 4 particles has some mass but no charge?
Neutrons.
This was the brainwave that a physicist named Leo Szilard had. He was literally walking across the street in London. He stopped in the middle of the traffic. Cars were honking. He suddenly realized he'd figured out a way to split an atom. And he also realized that it could be weaponized, which bothered him. So, okay.
That's a good thing, right?
Here is a picture of a nuclear reactor.
Can I color the picture in?
First of all, there's a typo. We're going to see if we can spot the typo. And let me walk through what's happening. Give me a second. I'll come back to you. So we take uranium-235. Okay, folks, I need you to focus better because there's a lot of chatter going on. Okay? Yes, still, I need you to focus. Okay? Hey, folks, I need you to focus. Okay? So we start out with unstable uranium-235. We hit it with a neutron. That turns it into more unstable uranium-236, and it makes this nucleus unstable. It splits up, and it splits up into krypton, not the planet, but the element, 92, and barium-121. Did you spot the typo? What was the typo you spotted?
Well, I spotted 2. One was that both barium and, how do you pronounce that one?
Krypton?
Yeah, they both have a higher mass than other neurons.
That's because they're unstable, but actually there's a typo here. This mass is totally wrong. Can you cross out the 121?
Of course, it's an element and not
Okay? Then we have 3 neutrons, and here's how I can tell you that the mass for barium is wrong. Look up. What mass are we starting with? How much mass are we starting with?
I don't know.
How much mass are we starting with? Tabby. 236. Shh, quiet, please. How much mass do we have to finish with? 236. So right now I have 92. I have 1, 2, 3 neutrons. That gives me a mass of 92 plus 3. This here, barium, has to have a mass of 236 minus 95. There's the 92 plus 3 is 95. And so the number that I'd like you to put there, it's unfortunate, there's a typo in the diagram that I stole from the internet, is 141. Can you cross out the barium and replace it, cross out the 121, replace it with 141?
You are correct. It is 141.
It is.
Wow. Great.
Mr. D with the big brain plays.
Here's how we would write this as an equation. Okay? This is going to look really intimidating. It's not too bad at all if you follow the steps. We're starting out with a neutron, so that's going to be N, mass of 1, charge of 0. Plus uranium-235, I would write that with a U, a 235, and a 92. And here's the key idea. I'm starting out with a mass of 236, and I'm starting out with a charge total of 92 plus 0, 92. At the end, I'm going to have the same mass and the same charge. So that's how we're going to track the numbers through. The first part of this, uranium-235 plus a neutron, gives us unstable uranium-236. So still a charge of 92. We've got an extra mass. But we still have 236 and we still have 92, check. Now the atom splits up. It's going to split up into krypton. And the krypton is going to have a mass of 92. And the krypton is going to have a charge of 36. The 36 I got from the periodic table. Krypton is element number 36. And barium. Barium is element number 56.
That's 238.
What here, 236?
Oh, I thought that's a 238.
Nope, 236. Barium has a mass of 141. If I look at my calculator, right now, if I add up the charges, I get 36 plus 56. That gives me 92. My charges match, 92 along the bottom. But if I add up my masses, 92 plus 141, I get 233. Nick, what mass do I want to end up with? Not 233. I want to end up with 236. What am I missing? 3. So what I need is a particle that has a mass of 3 and no charge. 3 neutrons. No charge. And each neutron has a mass of 1. So we would say plus 3 neutrons. And then we're going to add one more thing. Plus, you also get energy. Heat and light. Kaylin, put your phone away, kiddo. Okay? Need you to focus.
We can't focus when it's drilled into our brain.
So he does have a good point.
Yeah, even when it's drilled into
But I also say as a 15-year-old, you got to suck it up sometimes and butch through.
Okay, well, we
Okay?
Oh, so now you're assuming our
wow, really?
age.
Put your pencils down, look up. And this is what started what we call the atomic age. So, some important features of a fission reaction. I put some stuff on the next page. In neutron bombardment, a nucleus of uranium is hit by a neutron. That makes it unstable. Two smaller nuclei are produced. We had krypton 92. I think in the video you just watched, it was krypton 91. We had barium 141. In the video that you just watched, it was barium 142. There's some unstable elements. Fission can produce up to 5 neutrons. The most common is 3. A large amount of energy is released. A fantastically large amount of energy is released. The downside, the products, the resulting products are radioactive. And so this is what gives you what we call radioactive waste. Put your pencils down. So here's a couple of equations. You're going to want your calculator handy, or maybe you can do the math in your head. I don't know. It says find the indicated daughter nucleus for each of the following. So we start out with 1 neutron and uranium-235, and we end up with, well, first of all, our total mass to begin with is 236. I got that by going 1 plus 235. So I have to finish with 236. How much mass do I have right here? So on your calculator, go 236 minus 143. That leaves us with 93, but we're not done yet. How many neutrons do I have? Jada. So how much mass is that? 3. So I'm going to go on my calculator, 93 minus 3, leaving me with, so I have 90 mass left over. That's what's going to go up top here. Then I also have to balance the charges. The total charge I have starting out is 92. What's the total charge I have to have at the end? Same answer, 92. How much charge have I used up so far? 55. So on my calculator, 92 minus 55, 37. Now I need to figure out what the mystery element is. It's element number 37 on your periodic table. Which is what? Sorry? RB? So this is how you can figure out a nuclear reaction equation. It's a bit of detective work. It's a bit of calculator work. But again, you can get there by either adding or subtracting, depending on what they want you to find. Let's do B. Here's another nuclear reaction that can occur. Again, we're starting out with a total mass of 236. So what's my total mass going to be at the end? 236. So on my calculator, if I go 236 minus, I have 94 in the molybdenum, right there. And then it looks like I also have 3 neutrons, so that's 3 times 1, a mass of 3. How much mass do I have left over? So that's going to be a mass of 139. Now we look at the charges. I started out with a charge of 92. Plus 0, but 92 plus 0 is still 92. What's the charge that I have to finish with? Still 92. So I've got a charge of 42 here. It's going to be 92 minus 42, which is what? And so it's going to be element number 50. 10? That's the weird way. SN? I can never remember that symbol. Okay. What's another product of a nuclear reaction? So we can get cesium and rubidium. We can get tin and molybdenum. We can also get, so here again, we're starting with a mass of 236. So we have to finish with a mass of 236. So if I go 236 minus 140 minus 3, I have a mass of 93 left over. Charges, I'm starting with 92. I've used up 60 of the charges there. Neutrons have no charge. So it's going to be 92 take away 60. This element has a proton charge of 32. It's got 32 protons. So what element
That
number?
would be germanium.
Germanium? What's its symbol?
G.
Just a capital G?
Capital G and lowercase e.
Oh, GE. Okay. Germanium, named after Germany, because that's where it was discovered. Okay. You see how we balance these? This is why you need a calculator. You might be able to do it in your head, but I would use a calculator. The tricky part is you have typically 3 neutrons, each of which has a mass of 1 and no charge. So it's a little trickier. Yeah. Let me go a bit longer and then yes. Okay. We're going to nuke someone in a second. Okay. First of all, put your pencils down. But you can also, I'll show you how you can run these numbers for yourself as well. Okay? Oh, put a hand up is what I was looking for, not blurting out an answer. So there. Why do I think that nuclear power is such a part of our future? And the answer is one equation. You may even have heard of this equation. It goes E equals. So you've heard of this, have you? This is probably the most famous equation in history. Albert Einstein is the one who published a paper on it. And here's what it means. First of all, the E stands for energy. What this says is that all matter can also be converted into energy, into pure energy, typically heat and light. The M, can I, what?
I can't see the question that well. Can you zoom in a little
I
bit?
can try a little bit, but I can't do too much. The M stands for the mass, has to be in kilograms, not pounds. And C is the speed of light. Now, it's kind of weird, Mr. Dewick, why does the speed of light show up in this equation? And I'll just say, because light is special. Take Physics 11 if you want to find out more. The speed of light is a number. It's a 3 with 8 zeros. It's 300 million meters per second. Yep. Light's the fastest thing there is. It's the cosmic speed limit. Pardon me? Sorry.
There's a theory that the universe expanding faster.
It's not a theory, it's actually been proven. The universe is not just expanding, it is speeding up. So if you've ever heard the term dark energy, it's speeding up, which means it's gaining energy. Dark energy is the placeholder. We don't know where the energy for the universe speeding up is coming from, so we gave it a name. We called it dark energy. Once we figure out where that energy is coming from, then it'll probably get a different name. But if you've heard, and dark matter, there's also a bunch of unexplained gravity in the universe. We don't know where it's coming from. If you add up the amount of dark energy and dark matter, you can calculate it, that's about 95% of the universe. So right now, we don't know what 95% of the universe is. Hashtag nerd trivia. Jaden.
It is dope.
If what's the best thing in the universe?
Yep.
The darkness get there first. Didn't you just explain this? Why am I even asking this?
Darkness is the absence of light, but we'll talk about the Big Bang Theory and how that works later on in this course. Okay?
I love that TV show.
The scientific theory that posits the origin of the universe. So let's nuke someone. Okay? You're going to need to get out your calculator. So let's suppose we took all of the protons and neutrons and electrons that make up TABI, and using E equals mc squared, we converted them to pure energy. How much energy is there? So TABI's mass was 64 kilograms.
Wait, how are we supposed
I had a scale out, you were here, and if you want to, you can stand on the scale and get it.
I don't want
I'll bring it out.
scale.
Okay.
I don't want to stand on the scale.
So, if we want to figure out how much energy, it's going to be 64 times a 3 with 8 zeros. And then you can either find a squared button if your calculator has that,
Wait, I do want to stand
or
on the scale, actually. Where's the scale?
I'll do it. Sadie, we'll bring it out in a second. Or you multiply by the 3 with 8 zeros again. So I have a squared button on my calculator because I have a scientific calculator. So if I go 64 times a 3 with 1, 2, 3, 4, 5, 6, 7, 8 zeros squared, I get an answer that's too big to fit on the screen. My calculator says 5.76 and then E18. What does that mean? It means the answer is a 5, a 7, a 6, and then 16 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
I think there is. I forgot about
Million, billion, trillion, quadrillion, 5.76 quintillion, since you asked.
Wait, that's a word?
And we measure energy in joules.
Haha.
Okay. Here's the problem. That number is way too big for me to wrap my brain around. So what I'd like to do is I'm going to teach you a tiny bit of physics. This is not going to be on your test, but I'm going to convert this into how many 100 watt light bulbs for a year. How would I do that? If I take this answer, I don't want to write this out, so instead of writing this number out, I'm just going to put the capital E, and wherever you see the capital E, we'll put that number. I'm lazy. If I take that capital E and I divide it by 100 watts, that will tell me how many light bulbs it would light for a second. If I divide it by 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365. So if you have this number on your calculator, and you use your answer button and go divided by 100 watts per bulb, 60 minutes in a second, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. If we nuked you, Tabby, if we took all of the energy that was in your atoms and we turned it into pure energy, we could light that many light bulbs for a year. How many light bulbs is that? It's a good question.
A lot.
it. 74.
I'm going to cheat. Do that. Haha. So this is 1, 8, 2, 6, 4, 8, 4, 0, 1, 8. If I put the commas in, we could light 1.8 billion light bulbs for an entire year.
Weak.
By a single
Okay.
lead.
Can I?
That's why nuclear power, I think, is such a part of the future. The amount of energy you're talking about is ridiculously off the scale. Yes, nuclear waste. Yes, the possibility of accidents. Yes, as we give certain countries that are less stable nuclear reactors, it's possible with time they could turn that into a nuclear bomb. But in terms of bang for your buck, that's a lot of energy.
Oh well, it's a discount.
Okay?
Oh, can I try? I want to calculate.
Later on, I'll walk you through it. Put your pencils down. Sadie mentioned. So here's the other type of nuclear splitting of atoms. It's the opposite of splitting of atoms. It's combining atoms and forcing them together. Turn the page in your notes. This is the one that probably we'll get good at in the future. This is the type of chemical of nuclear reaction that's going on inside stars. Fusion. So unlike fission, where we take a big atom that's unstable and split it apart, in fusion, we take two smaller atoms, two smaller nuclei, and we join them together to form one bigger nucleus. And in doing that as well, we get some energy. How much energy? Look at the sun. A lot of energy. And more importantly, little or no nuclear waste. So this is the process that takes place in the stars or in the sun. So far, we can't do it without using more energy than we put in. So right now, it's not yet cost effective. There is a company in Burnaby that has a fusion reactor, and they're perhaps going to be one of the world leaders. They might get it done. They've got a pretty good board. There's some good physicists on there. It's very desirable, and the reason it's so desirable is little or no nuclear waste. So here's the equation of what's going on in the sun. And here's also how you can tell that it's a fusion equation and not a fission equation. We're starting off with small mass atoms. What's the H stand for? Hydrogen. In the sun, hydrogen has how many protons? 1. There's the 1. This hydrogen is called deuterium. It's got an extra neutron in its nucleus. This hydrogen here is called tritium. It's got an extra neutron in its nucleus. Inside the sun, under tremendous heat and pressure, these two hydrogen atoms, which would normally repel each other, can get fused together and become helium. Helium is the Greek word for helios, the sun, because helium was first discovered in the sun. And it gives off a neutron, but most important, energy, heat and light.
Does that say star?
Yep, stars. Here's what I want you to notice. Hang on, Graf. Here's what I want you to notice. We're starting out with a mass of 5. What are we finishing with? A mass of? Same rule as before. We're starting out with a charge of 2. What are we finishing with? A total charge of? So the same balancing trick as before, and this is why on your green sheet I said, where did I put this? In near the middle. For radioactive equations, the numbers on the right side have to match the numbers on the left side. Top has to match top. Okay, Oren? Bottom has to match bottom. We're nearly done. Put your pencils down, look up. So I included in your notes a little table about the key ideas. So we'll finish with this. We're almost done. So in a fission reaction, big atoms splits into smaller. In a fusion reaction, small atoms combine into one. And that's how, when you're looking at an equation, you can tell the difference. Look at your end products. Do I end up with 2 smaller atoms? That's fission. Do I end up with 1 bigger atom? That's fusion. In a fission reaction, we have unstable nuclei, and when they split, they give off energy. In a fusion reaction, we have lightweight nuclei. When they combine, they give off energy. I'll let you kind of read through the rest of this, but basically the summary is fusion probably is the future. We're trying hard to build fusion reactors. We're probably about 10 years away from getting them. If we can get that, that will take care of a big issue for energy. So I'm going to pause. I'm going to give you the homework. We are done radiation. Next class, you can expect a quiz, a take-home quiz. And it's a short unit, much shorter than the chemistry one. And next class on Thursday, we'll be watching a video on nuclear reactors.
Her birthday's on Thursday.
So this is based on an old Science 10 lesson. Quiet, please. From the textbook. There's certain questions that I skipped or covered over. So if you're wondering why there's black spaces, it means I didn't want you to do that question. So the first page, there's some vocabulary questions. See if you can fill in the blanks. Then on page 2, you don't need to do question number 1. You can skip that. Question number 2, I just want you to label the picture as fission or fusion. One of those you're combining atoms, one of those you're splitting atoms. That's just to get you familiar with the terminology. If you can't remember which is which, it's on your green sheet near the bottom of the page. Turn the page over. Here is balancing some equations. Some of these are fusion, some of these are fission. Oren, I need you to be quiet, please. So you need to decide whether they're fusion or fission, whether we're splitting or combining. I'll give you a hint. I think in number 2, it looks like that's fusion because we're starting off with small atoms and combining them into bigger atoms. I think number 1 is fission. We're starting off with big atoms and splitting them into smaller atoms. And then you want to try and fill in the blank numbers. Again, I attached the answers, but the key idea is all the masses have to add to the same total on each side, and all of the charges have to add to the same total on each side. And then the final page here are some multiple choice questions that you can answer as well. And then on the last page, I gave you an answer key. So you can expect a take-home quiz next class really similar to this. And later on, I'll also be showing you a couple more videos on whether or not cell phones cause cancer. We are done today's lesson.